How's it going? Oh, Michael, very close. This is Nintendo and lo-fi. But I definitely have listened to lo-fi hip-hop beats to study and relax to as well. Yeah, I can't get enough of this stuff. It's so perfect for if you're working on something, if you're studying, because it's not distracting, but it has a nice rhythm to it, so you can just groove, have some energy. Definitely enjoy it. Yeah, it's good stuff, my friend. Welcome everybody. I see people are trickling in. How do you guys feel about states opening up? You don't think it's a great idea? Yeah. I don't know. I mean, it looks like the numbers are tapering out, right? But then there's concerns for like a second wave if we just get out of control. I don't know. I don't know. It's definitely getting old though. I can get the frustration. I get it. It's such a drag to have like no human interaction. How's Erie County doing? Where are you guys? Are you still in Buffalo? New Paltz. Okay. Buffalo, New Paltz, Cattaraugus. Let's see. Western New York. Hey, look, things are getting better. Long Island. What does Mark Polencars have to say? Okay. Yeah, it'll be interesting to see with the different phases how this continues to look. But I think everybody's being pretty careful, right? Everybody's on board with the masks, it seems. I don't know, is that like it is where you guys are? I feel like in Buffalo, people are pretty much on board. Uh-oh, the Eternal Flame reopened. You guys seen the Eternal Flame? It is pretty sweet. I've only been in the like dead of winter. It's a nice little hike. My wife and I went there, like when it was still like real cold, snowy. We got lost. We were walking around for like 2 or 3 hours. Not fun to be lost. But it's cool, yeah, the flame back there, it's just always going. Trying to give a little bit of time for people to log in here. Are you guys new to Twitch, or have you used this before? If you want to interact with the chat, you have to make a free account. Don't worry, you don't get spammed and whatever. First time, cool. Yeah, you make an account, and then the way this will work is I'll give this lecture. You can throw questions in the chat, and I'll address those as they come up. Twitch is great, much better than the programs the other teachers are using. No, it's a nice platform. What are other teachers using? Zoom? WebEx and stuff? So, that's right, Kevin. Right when the Twitch automatically saves these videos to my channel. Actually, I could show you. And then additionally, I'm going to put this up on YouTube because the videos don't stay forever. So like if you go to my Twitch, wait. Yeah, you can go to videos. Oh, it looks like a lot of the videos that I had before got taken down, but I also made a YouTube just so I could put those videos there. And so I'll also put our lectures up here. Because I was doing Twitch this last spring, so I'm starting to get my footing with this, and so I'll put all our lectures up here. All right, guys. What do you say we get started here? I don't know if you saw my announcement, but I'm going to use these handouts. Like if you go to notes on our UB Learns, and if you go to handouts, I'm posting like a little follow along thing. And this is how I'm going to be filling this in as we go. I know not all of you have printers. I know not all of you will be able to like totally take advantage of this. Or if you download the PDF, some of you might have like a Microsoft Surface and you can follow along with this. But either way, it's nice to have a little template so that you can see this is where we're going, this is what we're doing today. And in addition to the videos, I'm going to post the PDF all filled in. Because we're going to fill this in as we go through today, and then I'll post that finished product so you'll be able to see our class notes. So I got positive feedback on these handouts, so we'll just keep running with this. Let's see. Do you guys want to go through the syllabus real quick? Let's not spend too much time here, because you can always go back to this later. Let's zoom in. All right. So, as you know, we're going to meet here on Twitch Monday, Wednesday, Friday, 2 to 4 p.m. So that'll be our lecture time. And, oh, this is me. I'm Aaron Estes. And so I'm a teaching faculty in the mechanical and aerospace engineering department. So I teach. Have you guys had me in class before, any of you? Maybe not. I teach mostly junior and senior classes. Like, I teach road vehicle dynamics. I'm going to be teaching flight dynamics in the fall. I teach the 334 MAE Lab 1. I do this class in the summer. I do control systems, digital control systems, in the spring. And so I love dynamics. And so you'll see I'm pretty excited about this stuff, and I'm excited to share this stuff with you too. Office hours. I'll have office hours every single day, 4 to 5 p.m. Well, not every day, every weekday on Twitch. I've also been considering using Discord, but I'll let you guys know whatever platform we'll be doing for office hours. And if you can't make these times, 4 to 5 p.m. every day, you can email me. We can set up something. Like last semester, I set up WebEx meetings with people. Okay. I did put a textbook here, System Dynamics by Ogata. It's a really great book. If you can get it, I'd grab it. I have the 4th edition, but it really wouldn't matter what edition you get. We're not going to be doing homework out of this book. Like, I make up all my homework problems, and I post all my notes, but it's always good to have an additional reference to get more info. So I would get it. Yeah, that's that book right here. I won't read this whole paragraph. You can read this later, but you guys have taken some physics at this point, electromagnetism stuff, that was always a really hard physics class for me. The mechanics, physics. This class is about what happens with real life systems where you have many interacting types of systems, like electromechanical systems, like a motor that drives the wheels of something. That's a mechanical system coupled with an electrical system. Like think of Tesla cars, right? They have an electric drive system, and it's this mechanical torque driven thing connected with an electrical system. And so if you want to, say, develop a cruise control system for a Tesla, you need to be able to model those kinds of coupled systems. So that's like long term where we're going with this course. We want to understand the dynamics of electrical systems, mechanical systems, even a little bit of hydraulic systems. And then think about what happens when you start connecting them together. Because that's the kind of systems we have in real life. It's rarely just one or the other. It's a couple things mixed together. The way we model these kinds of systems is with differential equations. Howdy, UB math professor. Good to see you. We're just going through the syllabus. I know some of you might recoil with a sick feeling in your stomach at the word differential equation. But we'll try to break it apart piece by piece and make it a little less scary. But we're going to be doing a lot of differential equations, guys. Let's talk about grading a little bit. Some of you will probably like this, that we're not going to have any tests. The reason I'm not doing that is because it's tough to regulate. All the differential equations you're seeing have solutions, right? They will have solutions, UB Math Prof. You better believe it. I'm not doing tests because it's really hard to regulate. So we're going to do a lot of homework. That's worth 70% of your grade. We're going to do probably, if I could, I would have a small homework every class period that'll be due the next class period. So I'll try to do that, but it might not happen every single class session. So don't miss those homeworks. I know some classes homework's not worth a lot. This class, you can't afford to miss any of the homeworks. You got to do all of them. So we're going to have homework. We're also going to have projects. So a project, it's going to be like a homework, but it's going to be a little more complex than the typical homework you get. A little more involved, more steps. All of these are individual assignments, by the way. So you can, of course, like collaborate. Well, we need to be careful there. You can if you're stuck somewhere and you have a friend, it's good to be like, dude, do you know how to like get through this problem or whatever? And you can talk to me as well. But I'm going to be grading everything for this course. And if things come in and I tell that something's just blatantly copied from somebody else, I'm going to give both of you no credit. So I'm a real stickler for that everything has to be your individual work clearly, and that's what we're going to do. These are our grade cutoffs. If you get more than 90%, that's an A. And then the rest follows from there. Academic integrity, that's what I was just talking about for this class. Everything in the end, it's got to be your own work. If you require any sort of accommodations, like note-taking, we're not going to be doing tests, so we won't really need the testing center or anything. But if there's certain accommodations you need, let me know. Topics. A lot of differential equation stuff. How to solve differential equations and analyze them. And modeling different types of systems. As I mentioned, mechanical, electrical, hydraulic, and what their dynamics look like when they're connected together in different configurations. Do you guys have questions about the syllabus? I just did a real quick glance over, because you can always go back to this. Ooh, let's get into today's content, people. So like I said earlier, this handout If you want to follow along, it's on UB Learns. I posted it under the notes section. Will there be a single project or a couple of them? Great question, Kevin. I'm planning on having 2 projects. The first one, I'm anticipating being around the halfway point, so 3 weeks from now. And the last one being at the very end, so right before July 4th weekend. What other questions you guys have? You're very welcome, Kevin. Okay. Today, we're going to talk about first order system dynamics, and I have a demo for you as well. Is this an accelerated summer course or something? A random lurker? Yeah, it's accelerated. Welcome, Eric. All right, guys, the simplest type of dynamic system we're going to look at this semester is a first order system. And I'm going to get right into a physical example. I like to do hands-on demos as much as I can to connect these concepts to real life. So we're going to analyze an RC circuit. So the R stands for resistor, and the C stands for capacitor. And let's draw a schematic. You guys have probably seen a circuit like this in a physics course or a circuits course. Okay, so we have a voltage source over here. So I'll call that V sub S. And it has a positive and a negative terminal. And then this jaggedy looking thing at the top, this is our resistor. And it has a resistance R. And then over here, these 2 flat plates separated from each other. This is a capacitor with capacitance C. The way you can tell the difference between a capacitor and a voltage source is I'm going to make the top plate on the voltage source a little wider, and I'll always put like a plus and minus. And that'll be missing on the capacitor. And so this is like the abstract schematic, but below this, here is a real RC circuit. I took a picture of it, but I have it here on my desk. I'll show you in a second. So here, maybe I'll get a different color. This, well, that's not showing up as well. Let's just do red. This is the resistor. And the resistance of this is 1 kilo ohm. All right. And then we have our capacitor right here. This big drum looking thing. So C. And this right here has a capacitance of 1 millifarad. And these red wires, this is the stuff that's powering the circuit coming in. So I have the plus, I have the minus, and the voltage difference between those wires. That's the source voltage. So we have like a path going like this. Swoop. Into the capacitor, it's storing in there, and then the current's coming out this way, goes this way, and back to the source. I'll show you. It's on my desk. There we go. This is the RC circuit. And do you guys know what this guy is? Have you worked with one before? I'm a big fan of this thing. What is it? Have you guys seen that before? Ian, yes. Okay, so you're a 334 student. Did anybody else take 334? Or is Ian the only one? It's an Arduino. So I'm going to be supplying the source voltage from an Arduino over here. All right, so what I'm going to be doing is, as a function of time, I'm going to modulate the source voltage. And what I want to do is I want to see how voltage gets stored on the capacitor. So the voltage across the capacitor. And what the source voltage is going to look like is it's going to be 0. And then at a certain time, let's say at time equals 0, I'm going to turn it on to 1 volt. And the capacitor, it's going to be 0 until we flip on the source voltage like a light bulb. But I don't know what's going to happen. But that's what we're going to do. We're going to study how voltage gets stored on this capacitor. That's our first problem of dynamics. Are you guys excited? Okay. Now, this kind of function for the source voltage that I'm showing up here, it looks like a staircase. It is called a unit step function or a Heaviside function. I'm going to give you the definition of a Heaviside function. So it has usually they use like this scripty h for the Heaviside function as a function of time. And it equals 0 if time is less than 0, which we saw up there. And then it equals 1 if time is greater than or equal to 0. So that's the definition of a Heaviside function. Just like a quick example. Let's say if the source voltage is 0, and then turned on to, let's say, 5 volts at time equals 0 seconds. Let's write a function for the source voltage as a function of time. So in this case, we would say the voltage, we said it was 0 for time less than 0. And then it got turned on to 5 volts at t equals 0 seconds. Well, if this is the case, you could just say that the function for the source voltage is 5 times a Heaviside function. Okay. So we have our RC circuit. I want to provide a source voltage, which is a unit step function, also known as a Heaviside function. So I'm going to turn it on to 1 volt. And I want to see what happens with the capacitor. So let's run an experiment. Are you ready? We're going to plug this in. Oops. I'm going to open up the Arduino software. And in this class, you don't have to worry about Arduino and how you program it, whatever. I'm just showing you this because this is what I'm using to get measurements from this RC circuit. All right, let's comment this out. Let's upload this to our board. And then I'm plotting the source voltage and the capacitor voltage. So give it 1 second. The blue line, that's the source voltage. So I turned it off, and then the red line is the capacitor voltage. So you see when I turn on the source, the voltage in the capacitor slowly fills up. And then when I turn off the source, it drains the capacitor again. Turn it on. Turn it off. And I'll get the camera down here. But I mean, nothing is... Oops. You won't be able to see anything physically happening, but it's just letting you know that we're storing voltage on the capacitor right here. it's not getting warm or anything. The resistor, but we're measuring from this in real time. All right, let's go back to this. So what I did before I booted up Twitch today is I ran that same experiment in Arduino, and then I saved the data to a text file, and then I imported it into MATLAB. So this that you're seeing is the same data that we were just recording. I'm going to unplug this. All right. So source voltage in this case is in red. The capacitor voltage is in blue. And you can see that the source voltage is alternating between it's turned off and then it's turned on. And you can see in real life, it's hard to create like a perfect step input. There was like a little bit of delay here. You can see where it had to get up to 1 volt. But let's introduce some terminology. The first one that I want to look at, because some of the others depend on this, is the final value. So in this case, the final value is, the value of VC as time approaches infinity. Well, we never really gave it that much time. When the input, actually let's call it, when the source voltage is fixed. So for this experiment that we did, there's actually 2 different final values that we're alternating between. So when the source voltage equals 0, what's the final value of the capacitor? And I'm asking you guys, throw it in the chat. This is just a test if people are actually awake. So when the source voltage is 0, what's the final value? Brilliant. Thank you, Michael. The capacitor voltage is also 0. You can see it's tending towards 0. And when the source voltage equals 1, we have the capacitor voltage tending towards 1. Actually, let's be precise here. When the source voltage is 0, the limit as time goes to infinity of the capacitor voltage is 0. That's how you specifically define the final value. And when the source voltage is 1, the limit as time approaches infinity of the source voltage is 1. So simple enough. Settling time is next. And we needed to define the final value before we got to settling time. So we're going to define settling time in this way. The settling time is the amount of time it takes to get 98% of the way to the final value. And this can also be applied both when the source voltage is turned off and when it's turned on in this case. So I'll ask you again, looking at the capacitor voltage, looking at the time axes, maybe I'll zoom in here. What would you say the settling time is? So it's the time it takes to get 98% closer to its final value when it starts from like a rest state. Approximately 6 seconds. I would agree. So what we're saying is, so you could look at this in two ways. Like this is one starting point right over here at 10 seconds. So where the source voltage was on, and then at 10 seconds we turned it off. And that's when the capacitor started to drain its voltage, and then we're looking for when it gets 98% closer to its final value, which in this case, it's tending towards 0. And, you know, it's kind of guesswork at this point, but I want to see when it gets to, so 98% closer would be when it's at 0.02. And if I kind of like drew a line across here, I don't know, that's kind of rough, but it would intersect. So the settling time, which we can call T sub S, it's somewhere between 5 or 6 seconds. So that's the time from here to here. Same thing over here. Right at 20 seconds, we turned on the source voltage. And then once it gets to 0.98, which is 98% closer, once again, settling time, 5, 6 seconds, I don't know. Okay, simple enough. We're just defining some terminology here. The time constant. The definition of this, we call it tau. So like the Greek letter tau. It's 1/4 of the settling time. And the settling time is T sub S, so we could call it TS over 4. So in this case, like let's say the settling time is 6 seconds. So we'll say it's 3/2 of a second. And let's just leave it at that for now. So settling time and time constant are related to each other. It gives you an idea of how fast a dynamic system is. Okay, 2 more terms that I want to get through. The homogeneous response and the forced response. So the homogeneous response, these are the system dynamics when no external forcing is applied to the system. So you might say, okay, if there's no force being applied to the system, then I know Newton's laws, like nothing's going to happen to the system. Well, you're right, but unless the system has some initial state that's different from its like equilibrium resting state. So in other words, this is how the system responds to non-zero initial conditions. Like if the capacitor had nothing stored on it and no source voltage is being applied, then the capacitor will just sit there doing nothing. However, we have here, so from 10 seconds up through 20 seconds, this is a homogeneous response. Where the source voltage is equal to 0, but VC, the capacitor voltage, equals 1 at 10 seconds. And those are like the non-zero initial conditions. So it had some voltage, and now it's dissipating that voltage with no external forcing function being applied. Okay, a forced response. This one's easy. It's just system dynamics under the influence of external forcing. And that doesn't have to literally be like a force, like you're pushing it. In this case, a forcing is injecting voltage and current into the system, and it affects the dynamics. So at 20 seconds, when we turn back on the source voltage, this is a forced response. Okay. So in our little experiment, we were applying a unit step input. When we look at the dynamics, we can assess a couple things. We can say, okay, what's the final value of the system? What's its settling time? How quickly does it get there? And we can also look at the homogeneous as well as the forced response. Okay, now I want us to study this system like a little bit more to get an idea, a little more of an intuition about how RC circuit works. So what if we change out the resistor? What if we change out the capacitor? All right. So we're going to run a couple more experiments. Let's come over here. Okay, so I have a couple different resistors. So right now we have 1 kilo ohm in here, but I want to try this 220 ohms. So it's a lot less, or like 5 times less resistance. What do you think 5 times less resistance is going to do to the speed with which the capacitor fills up? You think it'll make it slower or make it faster? Slower, faster, faster, slower. Would you bet your life? Would you bet your very life on your answer? Okay, I plugged in the 220 ohms. You would bet your very life on it, Michael. I like that confidence. Okay, so it was like 5 seconds before. More current into the capacitor equals faster charge. Okay, that's a theory. Let's run this. Upload. Okay, we'll go to the plotter. Okay, we have to wait a little bit. Ooh. Okay, the way we're gonna... So it looks faster, right? Wait, what did you say, Michael? Did you say... You said... Okay, good. You get to live. Kevin, I'm sorry. You've just forfeit your life. Wait. Let's go to... I'm going to print how much time has passed, so we can get a number out of this. So the first column is time. The second column is the source voltage, which just goes between 0 and 1. And then the last column is the capacitor. So we're going to turn this off and let's... So how long did it take to get to 0.2? Or 0.002? Okay, so at 10 seconds, we turned off the source voltage. And then the capacitor voltage started draining. And then it got to 0.02 at like 0.96 seconds. So 0.96. All right, let's do a couple more of these. So that was 0.22 kilo ohms, or 220 ohms. Let's do 470 ohms, so we'll like double it. Okay, you get another chance, Kevin. So we expect this. I just plugged it in. We had 0.96 seconds. Let's put... And we had like 1.5 seconds when we had 1 kilo ohm. That was the original one. So this is interesting. It was like 5 times less resistance, but it wasn't 5 times faster per se. So it's not like a totally linear relationship. Okay, let's try this 470. I think I can just do this. Okay. Let's wait for this to turn off and go to 0, and then we'll do a count. Oops. Okay, we're looking at when the third column gets down to 0.02, and that was 1.88 seconds. Wait, hold on a second. Wait, is that that's slower than the... Oh, 1 kilo... Oh, right. Oh, the time constant is 1.5 seconds. Oh. Never mind. So it is like 1 kilo ohm is like 5 times slower. All right. So what do you think 2.2 kilo ohms is going to be? Like 10 or 11 seconds? All right, real quick, we'll do it. We got these resistors. I'm plugging this sucker in. Okay, 2.2 kilo ohms is in. Let's run this. Okay, so at 10 seconds, it's going to turn the source voltage to 0. Oh man, this is taking a while. Okay. Eight point 8.3 seconds. Okay, so what are we learning? If you increase the resistance before the capacitor, so there's our resistor. If you make that a juicier resistor, then the capacitor is going to charge slower. What do you think happens if I make this capacitor smaller? This is the biggest capacitor I have, actually. I have like a little box. Let's see. Here's a box of capacitors. That was the biggest one I had. What if I take this guy a little bit smaller? So maybe we'll just try one of these for the sake of time. We won't do as many variations. What did I put over here? 0.47 millifarads. So that's like half the capacitance. Oh wait, no, I'm doing point. No, let's do 0.47. All right, what do you think is going to happen? So this one was the original, and we had like 5 seconds. Now I'm going to cut that capacitance in half. What do you think is going to happen? And you have to bet your life on it. I have to clip the ends of this a little bit. It has 2 legs. Okay. Faster charge and discharge rate. Okay, it's a smaller capacitor. You can think of a capacitor like, I don't know about betting my life on it though. Okay. That's all right. Let's look at the plotter first. Uh-oh. Did I break this? Oh, I think I have to suppress this first. All right, come on, come on. Huh. Let's look at this, the text output. Okay. Oh, I have to re-upload this. All right, serial monitor. At 10 seconds, the source voltage will turn off. Okay, it was like 3.8 seconds. Okay. So that makes sense too. If you have a smaller capacitor, it takes less time to fill it up. Think like filling up a smaller bucket of water. So I increase my system speed by making the capacitor smaller. I also increase my system speed by decreasing my resistance. Okay, so we're just running experiments. We're building understanding. Oh, maybe I put a little conclusion space in here. Let's fill it in. Smaller resistance. Faster settling time. Smaller capacitor. Also faster settling time. Fills up faster. Okay, well now I have a question for you. So we've run some experiments, all right? We have a general idea of how the trends work. What if I asked you to make me an RC circuit, but I want the settling time to be 1 second? And further, I'm telling you that the resistance, it has to be 5 kiloohms. So, what do you choose for a capacitor? And maybe I'll pull that table up for a little help. And I want to open this up to you guys. Like, what are your thoughts? Like, having done what we've done so far, what would you do? And I'm not asking for the exact answer. Tiny capacitor. Okay, let's think about this. So, okay, good. Like, we see that as we increase the resistance, it makes the settling time slower. So we didn't even get all the way up to 5 kiloohms, but I mean, it doesn't look like it's totally linear how the settling time increases, but we can definitely bet that if I leave my capacitance at 1 millifarad, which is what we started with, I don't know, I would guess the settling time to be like 16 seconds or something. Right? So, we know that the smaller we make our capacitor, the faster the settling time of our system is. So this is 1 kiloohm. Yeah, I mean, I think, Eric, you nailed it. You can definitely say that we're going to have a much smaller capacitor. But unless we run more experiments, it's going to be really difficult to figure out what that capacitance should be. Like, I don't even have in my capacitor kit or my resistor kit a 5 kiloohm. So I'm just trying to put you in a situation, like a real life situation, where you have some constraint, and what are you going to do? Like, I don't have a 5 kiloohm resistor to test so that I can run through different capacitances and find a trend. Actually, I can mix and match resistances, put them in series and whatever to probably dial it in. So, smaller capacitor. Well, smaller than 1. Actually, we could probably say it's smaller than like 0.47 millifarads. But from experiment, it's not totally clear how small it should be. So more testing would be required. So there's 2 reasons I wanted to start the class with this example. For one, or maybe more than 2 reasons, but this is a real life dynamic system, RC circuits show up in lots of different devices. What was I going to say? Do you ever have those instances where your brain just totally evacuates? Right. I wanted to show you this because it's a popular system, and I wanted you to have an idea of how it works. So like now, if somebody asked you about an RC circuit, you've seen how it responds, how voltage gets stored on the capacitor. You know what it looks like just watching it in real time. And you also know how resistance and capacitance like has a general effect. I think as an engineer, it's important to have those kinds of basic intuitions about the dynamics of a system to solve problems. So like Eric being able to say like, oh, we're going to need a smaller capacitor. That's a really valuable insight, okay? But I also wanted to show you this to say that tinkering around with the system to figure out these general trends, it might not be enough when somebody asks you to solve a more specific problem like this one. Like maybe a certain application requires a capacitor to be charged in precisely 1 second. And we have some constraints, like I only have a 5 kilo ohm resistor, that's all we can get our hands on. So what do? It's hard purely from experiments and intuition to know exactly how to solve that. And that's kind of the purpose of this class, to fill in those gaps with mathematical models. And the specific type of mathematical model you need to answer this question is a differential equation. Let's list some reasons why we need mathematical models. So I would say number one is to predict results that we can't get with an experiment. Or maybe you could get those results with an experiment, but it would be expensive or costly. Or maybe I'd have to order a new resistor on Amazon. It'll take like 3 weeks to get here, you know. So predict results that we can't get with an experiment, or that would be difficult or expensive to get with an experiment. Another reason for mathematical models they enable us to design system with certain performance requirements. So not like a trial and error approach. It's more like I'm going to use a model, and that's going to help me get a very good idea of what I need And then I can go back later with an experiment and kind of dial it in. And maybe there's some more reasons we can think of and fill this in later. All right, we've been going for about an hour. And I think we should take a 5-minute break. So for me, it's 3:17 Eastern time. You ever feel like your days are more like dreams? Sounds like it's from a song. All right, and we're gonna come back at 3:22. All right, and the second half of the class, we're gonna mathematically model the RC circuit, and we're gonna see if it behaves like the real life system. So that'll be cool. So I'm gonna go to intermission. I'm gonna turn up this music a little bit. I'm gonna turn on the air conditioning. I'm starting to burn up. See you guys in a little bit.
Lego.
All right, are you guys back? Jumping plumber guy. There's definitely some Mario. What's up, Falcon? Why do I hear Mario noises? I don't know. I think it's just you. I think you're hearing things. I think you're hearing things. Are you guys ready for some mathematical modeling? Let's get right into it. So, we have our circuit. And this is Kirchoff's loop rule. The sum of voltages around any loop in a circuit is 0. And there's another way of saying this, which I think is a little more specific. The sum of voltage rises and voltage drops is equal to 0. Also, you know, going around a loop. So what that means, that we're going to unpack this. But if you were to walk around this RC circuit in a loop, going that way, or you could also go in the opposite direction, walking around the loop, and as you encounter each circuit element, if you sum the voltage rise or voltage drop across that component, if you add them all up going around the loop, it's going to go to 0. And that's going to be like the key method we're going to use to model this. So let's unpack that. What are voltage rises and voltage drops? And how do we add those up? So what I want to do, I want to show you how this works for the 3 different components we find in the RC circuit. So we have I'm going to put a voltage source here. Let's say that's the plus. This is the minus. So it's the same as what we have in our RC circuit. I've just flipped it on its side, okay? So that's our source voltage. It's like a battery. And let's put 2 points, A on the left side, B on the right side. If I want to find the voltage from A to B, so in other words, going from left to right, this is going to be minus Vs. In other words, it's going to be a voltage drop because I'm going from the positive to the minus terminal, and I'm going to lose voltage across that, okay? But if I go from the other direction, from B to A, I'm going to get a voltage rise. So positive Vs. So if our loop goes from one direction or another, that'll change if you get a rise or a drop. Let's move on to a resistor. So we're going to do all three components: a source, a resistor, a capacitor, and then we're going to put it all together. A, B. Here's our resistor. And let's say the current is flowing left to right. The direction of the current is important. So, okay, let's say the current's flowing left to right, and I want to get the voltage from A to B. This is going to be minus R times the current. Let me make a little side note here, just to be clear. When I say like from A to B, this would be the voltage at A minus the voltage at B. So, wait. Am I confusing myself? Okay, we get no, I think it's the other way. Yeah, it would be voltage at B minus voltage at A. Because as we go across this resistor, we lose voltage. So the voltage at A is higher. Okay. But what you need to take away with this is as you cross a resistor in the direction of the current, you're going to have a voltage drop as you cross the resistor. Okay, but what if I had my loop coming from the other direction? Then it would be positive R times I, and I would have a voltage rise. Let's do a capacitor now. A, B, the capacitance is C. And we're also going to put the direction of the current here, because that's important. So let's say we're going from A to B. Just like a resistor, we're going to lose voltage as we cross that capacitor. The voltage that we lose, and don't get scared by this integral. We're actually not going to use it very much. We're actually going to use the differential form. But I think having seen our experiment earlier, this can kind of make sense that over time, the voltage in a capacitor can build. All right. And an integral is like a summation that's adding up things as they accumulate. So that's how this can make sense to me. The voltage buildup across a capacitor is the accumulation over time of current flowing. Now, if you go in the direction opposite to the current, so from B to A, it's going to be positive. Now, so we don't have to rewrite this a lot. I'm going to call the positive version of this just VC, the voltage change across a capacitor. So I'm just going to make that as like a definition. That's what that triangle means. I'm going to do the same thing with the resistor, like this Ohm's law, resistance times the current. We could call that V sub R. What's the triangle mean again? The triangle just means like a definition. When you see an equal sign with a triangle on top, it just means I'm defining VC to be equal to this integral. Oops. Same thing here. I'm just saying by definition, I'm going to say VR is R times I. You're very welcome. And once again, guys, don't be shy. Ask questions at any time. I love to answer your questions. And sometimes I'll make mistakes. I'll try to limit those. But if you see something, like Michael saw something earlier, I messed up the settling time. I appreciate it if you see something and point it out to me. Circuits can be intimidating. I know that. That's why I wanted to start with some of this on the first day. And we'll just keep coming back to it a little bit and practice it a lot. And it helps the more examples we do. So we're going to use these definitions and we're going to apply it to the RC circuit. So let's just draw it one more time. I'll draw it like this. Voltage source, resistor, capacitor. And I'm going to define a current going this way. But it doesn't matter which way you define that current, because we're going to end up with the same equation in the end. This will become more relevant once we end up having to work with some circuits that have multiple loops. But just remember, we're defining a current variable throughout here, and you don't have to worry which way you put it. Everything will work out in the end. All right. And how about we define some nodes? Or these aren't nodes, but these are points to use to define these voltage drops. So you'll see how I use these. So let's apply Kirchoff's loop rule to this. So what it says is the sum of voltage rises and voltage drops is going to be equal to 0 as you go around the whole loop. And so the loop that I'm going to do, I'm going to go from A to B to C back to A. And you don't have to go this way. You could go the opposite direction. It could also work. You just pick one. So we know that the voltage drop from A to B, or whatever it is, whether it's a rise or a drop, plus the voltage change from B to C, plus the voltage change from C to A, that has to add up to 0. So that's the loop rule. And now when we're asking ourselves, okay, what is it from A to B, B to C, C to A, go up to the table we made. I probably won't be able to fit it all on one screen. Oh, I guess I can. It's a little small. But let's start with a voltage source. If you're going from... So we're going from the negative to the positive terminal. And that means we're going to gain voltage as we go that direction. If you look up here, well, we had the negative terminal on this right-hand side. But it's just like this. Going from B to A, we get a positive Vs. All right? So here we're going from negative to positive. So this is going to be positive Vs. Next, we're going to go from B to C. So we're crossing a resistor. And further, we're crossing that resistor in the direction of the defined current. So we're going to lose voltage across the resistor. And I'll just go back up here real quick. It's actually identical to this case here. So we're going to have minus R times the current. Minus R times I. And then as we go across the capacitor, we're going to lose voltage because we're going in the same direction as the current. And I know that this voltage drop is equal to, 1 over C times that integral or whatever. But I'm just going to write that as VC. Because we defined VC to be equal to all that stuff. And so this is equal to 0. I should mention here, the goal of applying Kirchoff's rules and whatever, what we want to do, where you want to get a differential equation, which is, it's a mathematical model that relates VC to the source voltage. So we're building a mathematical model that relates the capacitor voltage dynamics to your source voltage. Okay, we're going to call this equation 1. Now, before we proceed, I want to go back up here. And I want to take this equation and take the time derivative of it. Path integral? No. We're just doing some basic time integrals. So we'll do that here. The time derivative of 1 over c will be the time derivative of vc. So I'm just taking the time derivative on each side. Now we're taking the derivative of the integral here, and that's not difficult because we're just left with 1 over c times I. That's by the fundamental theorem of calculus. And that looks a lot friendlier, doesn't it? Now, a notation that we're going to use in this class for time derivatives is called dot notation. So I'm using another definition. When you have the time derivative of vc, we just call that vc dot, where the number of dots represents the number of time derivatives. So this is an important equation that we're going to use for analyzing circuits. We'll call this our capacitor element equation. And this describes the dynamics of how we store voltage on a capacitor. So the rate of change with which we're storing a voltage, so the first time derivative, is 1 over the capacitance times the current going through. So if there's more current, then we're storing voltage faster on a capacitor. All right, so we're going to use this equation down here. And I'm going to call it equation 2. So what we're going to do, we have this this term for the current in here. We're going to solve for the current from equation 1, and then we're going to substitute it into equation 2, all right? So I is equal to Vs minus Vc over R. So if we sub that in here, oh, I should have put a dot on top of this VC. And then I'm going to rearrange this equation a little bit. I'm going to bring all of the VC terms over to the left-hand side. And I'm going to put these source voltage terms on the right-hand side. And this is our first differential equation of the course. So in words, this relates the rate of change of the capacitor voltage to the source voltage. And this is the key to analyzing our RC circuit. Now, here, let's point out the order of a differential equation. Because I'm calling this first order, but why am I calling it first order? The order of a differential equation is the highest derivative of the dependent variable. So that's VC in this case. So we just have a first order derivative. So this is a first order differential equation. All right. So here's the last thing we're going to do today. We're going to look at how you get the homogeneous solution of this first order differential equation. And along the way, we're going to get a mathematical expression for the settling time and time constant. And we're going to use that to answer the question we posed earlier. And we also want to see how good this model does at replicating the experiment we saw. Okay. So the first thing you should know, integrating factor. Yes. So solving a differential equation means returning the dependent variable, which in this case is the capacitor voltage as a function of time. And there's going to be two parts to the solution, and we're just going to focus on the homogeneous part. But so sub H, I'll label that in a second, but that's the homogeneous part. And then you also have the particular part of the solution. So this sub H stands for homogeneous, sub P stands for particular. And what I'm going to do, I'm going to take the first derivative of this, and you'll see why in a minute. So I would get the first derivative of the homogeneous, first derivative of the particular, because I want to show you what the difference between homogeneous and particular means. So what we're going to do, take this, substitute this into our differential equation. Which is, you know, right above. So for this first derivative term, I just have this. And then I have 1 over RC times homogeneous plus particular. And then that's equal to 1 over RC VS. Now, this may seem a little weird, but I'm going to put a plus 0 on this right-hand side. I mean, no matter what your differential equation is, you could always add a plus 0, and it wouldn't change anything, but this becomes important for the homogeneous. So the definition of the homogeneous part of your differential equation, so now I'm going to use blue for all these sub H terms, the homogeneous ones. And maybe I'll use this purple for the particular. I'm also going to use purple for this forcing function. So the definition of the homogeneous part is the portion of solution equal to 0. Or I should say portion of the differential equation so we'll just write out the homogeneous portion explicitly here. So given a differential equation with some forcing terms, like in this case for an electrical system, it's like a supply voltage. If you set that equal to 0, that leaves you with the homogeneous portion of the equation. Okay. Actually, you know what? Because we're a little short on time, and I want to make sure I don't blast through this too quickly, maybe we'll pick it up from here on Friday, where we'll actually solve this. So I'll make a note here. stopping here on 527. We'll solve this on Friday. And at this point, we'll be able to compare the dynamics predicted by this math to the real life experiment we did, which will be good. It'll be cool. I'll hang around here for a couple more minutes to take any questions you guys have. Could be anything. I'm going to give you guys a small homework that'll be due before class on Friday. And I think it'll just review some of the basic things that we went over today. Sound good? We'll turn up the tunes just a little. We'll pick up some momentum as we go. Will there be a folder in UB Learns for homework to upload? Yes. Let me go to UB Learns right now. Questions. Okay, so I'm gonna upload your homework here under the assignments folder. So nothing's there yet. I'm going to put up your first homework tonight. Won't be too long. My philosophy with the summer course is to just keep you constantly grinding on something. Keep your mind engaged with it. Put it up tonight. You'll submit it as a PDF. Like you can just write out your solution by hand. Use Cam Scanner or something on your phone. Snap a picture. Convert it to a PDF. Put it up here. So supposedly we're supposed to hear around June 1st what the plan is for fall. Whether it'll be like all online or if we're gonna be any rumblings. What's a rumbling? Oh, about the all I heard is that they're trying to, by June 1st, give us something. So hopefully we get more direction in the next couple days. Have you heard anything? Just what other... Yeah, right. We have the California system definitely online. I heard suspicions about grad students being allowed back on campus, but undergrad would be online. Really? I know for those grad students doing research, there are going to be ways for them to get on campus. Already they're able to get into research labs, or that's being unrolled like right now. Huh. A lot of math grad students have been on campus anyways. Yeah. I just don't know. This is interesting. Yeah, I think most people are still considering their options. I've also been in and out of chat trying to fix your mic issue. Oh. Ooh, did you see SpaceX is launching a rocket? That'll be on YouTube, right? Live streaming? Ooh.
Don't ever forget, wherever you go, I'm always with you. Even if we're apart, we're not alone anymore, right?
Yeah, with the crew. Do you know if is the rocket going to be reusable? Good question. Who are the astronauts? Who are the SpaceX astronauts? Oh, it's only 2 of them. Falcon, you have a good viral vid idea, but no idea how to fit it in. Ooh, what's your idea? I won't steal it. Robert L. Bankin and Douglas Hurley, whom NASA selected to be astronauts in 2000, which is 20 years ago.
It's my lucky charm. Be sure to bring it back to me.
Don't worry.
Oh,
Promise?
Promise.
Don't ever forget. Wherever you go, I'm always with you.
a gumdrop-shaped capsule, an upgraded version of SpaceX's original Dragon capsule. Fully reusable, wow. It has space for up to 7 people, but will only have 4 seats for NASA missions. That's what it looks like? That's a cool looking shuttle. 19 hours after launch, they will arrive. Wow. Wonder what other
Person going off to space on a SpaceX type rocket. So I think that's why the numbers are so high.
Yeah, and we are really thrilled to see all the folks watching along online. I know we certainly hope that that this
22
is a go,
minutes.
We're going to hear a little bit of a weather update in less than 3 minutes now. And Leland, you know, I know they're waiting for a weather update, and they've come, you know, almost all the way down the count. What do you think Bob and Doug are thinking about right now?
You know, we on 120 SES 129, we were having some weather problems, and I think we were getting close to the countdown, and then it seemed like the sky just cleared up right above our heads.
They
saw
look
it, and we knew
very
we were
chill.
going. And, you know, we always know that, you know, you can have any types of delays, fuel prop delays, all kinds of things that can happen, but we've trained over and over and over again for these types of scenarios. And so, you know, we want to be safe. We want to be safe for our families, and we'll, you know, do this another day if it doesn't work with the weather.
I love that John I always says weather. It's that thing that everybody talks about, but no one can do anything about it.
I know.
And it is this interesting thing of just, you know, succumbing to Mother Earth. She's going to tell us if we can go or not today.
Right.
Yeah.
Well, if it happens, I mean, look at it this way. Bob and Doug got one really great rehearsal in, right?
It's always best to practice and practice and practice, yes.
So we're 20 minutes out, and
So
they're still
again,
not sure if they're
we're
going to
less than
launch.
2 minutes now from that weather update that is going to go directly to Bob and Doug, and we will quiet down so we can listen in for that, because I know we can't wait to find out what that is, and those of you watching that have been following along, we are eagerly awaiting to hear whether the weather is going to be a showstopper today.
Weather the weather.
can seem really deceiving at times, right? You see the blue skies peeking through and you think everything's fine, but you just don't know. That's why we have those launch weather officers.
Absolutely, and I know, we've talked about it before, but it's not just the weather in Florida that they're looking at. They've got to look at weather downrange. If they were to have an abort in flight and they needed to come down somewhere in the ocean, they need to consider what the weather's like out there, because recovery teams have to go out and get them in a situation like that. So there's so many variables, and that's why not just with this flight, but with every human space flight we've had in the past, there's always a very good chance of a scrub, because you do have so much criteria that you have to meet. And we're going to listen in now. We're just seconds away from a weather update.
Stage 2, RP1 load complete.
That is liquid oxygen you see venting off the rocket. That's completely normal and expected. We're standing
Oh
by
dear.
for a weather update.
Unless you can give us another 10 minutes, I don't think we're going to get there with any of the rules today.
I'm going to give you 10 minutes.
I mean, another 10 minutes past T0.
Oh,
16:40. 16:45 local. I think we'll probably be clear on all the rules, but not quite going to make it for this.
Okay. We're going to check back in with you in about 2 minutes, and then I'll call it up at about T-minus 17 minutes.
Okay. Yeah, there's some of them are starting to count down, but we still have one above 2,000. So if that gets below.
Huh.
And that didn't sound great right there. That was the weather net going out, but we're still standing by for a final decision.
That last little sound clip made it sound like it was uncertain.
And we're going to continue to listen in for an update, but in the meantime, we're going to go over to John Innsbrucker at SpaceX headquarters in California. John?
Yeah.
And Dragon SpaceX on weather. We're still not
T-minus 18 minutes and counting.
LD is
We are still red
having some
on weather.
Expect an update from LD.
We're waiting in about another minute for one final check with weather. We're going to check at T-minus 17 minutes possibly. We don't really expect that things will have improved. The weather officer was not optimistic that the weather would clear up that rapidly. We did hear the launch director, Mike Taylor, joke that if we could move 10 more minutes past the T0, weather conditions may improve, but Mike was not able to do that. We have an instantaneous window today. So at 17 minutes, we want to make that call, because shortly after that, we will begin loading liquid oxygen onto the second stage.
Oh wow, we're like 20 seconds away from the decision.
The clock's going to run out. Stand by.
We continue to violate a couple different weather rules that we now do not expect to clear in time to allow for a launch today. We go ahead and end today's launch attempt. Launch control. Go ahead and end the launch auto sequence and proceed into the launch abort auto sequence, please.
Abort.
Launch abort has started.
Oh man.
And Dragon SpaceX, unfortunately, we are not going to launch today. You are go for 5.100 launch scrub.
5.100. It was a good effort by the teams, and we understand, and we'll meet you there.
Copy all.
We've heard the call from the crew. They have been informed. Launch director Mike Taylor has called a scrub for the day, and we got the feedback when the Dragon team informed Bob and Doug. They said we gave it a good try, but they understand, and we are here to try another day. So right now we did officially hold the clock. It looks like at T-minus 16 minutes, 54 seconds. The launch automatic sequence that controls the Falcon 9, the loading of propellants, the cycling of valves, that is also stopped.
Too bad.
It is a normal scrub sequence for us. We practice this every launch. So now we move into safely taking the propellants, the pressurization gases back off the first and second stages. As things get into a safe configuration, then we will disarm the escape system on Dragon, and we'll bring the crew access arm back around the spacecraft. So right now, we got down to just inside 17 minutes. The hardware was working.
Oh dear. All right, my friends. I'm going to call it a day. And I'll be here for office hours tomorrow from 4 to 5. And then we'll be back in class Friday. I hope you guys have an awesome day. See you, Falcon. See you, Michael. See you, Math Prof.